Okay, in the previous session we were talking about what tomography is and why you need multiple views of a certain object to be able to reconstruct its internal structure, which is essentially what tomography does. And we also discussed briefly the ideas behind radiography and what type of techniques you will need, and we worked through a couple of very simple examples that discuss this problem of unique reconstruction. So today we will start discussing some of the more technical details. The first step in this discussion is to look at what are called Fourier transform techniques. Now I understand most people have probably seen or even heard of this term before, but just to make sure that all of us are on the same page, I will introduce the Fourier transform step by step, and then we will see why it is central to our discussion of what is eventually going to be called the radon transform, and how the Fourier transform can be related to the radon transform, but we will get there in due course. Okay. The first step before we start on this sort of journey is to look at a simplified representation of a light path, right. So what happens when a light passes through a material? So for example we will take a 2D case, this is 2 dimensional, this is your incoming light. So I am passing X-rays like this is my object and my screen is here. Remember the screen is perpendicular to the light source, right. So if you remember our coordinates from the previous discussion, it was Z and this was XY. So this is, let us say, Y, does not matter, right, and this is again Z, but we look at one cross section of a material or a 2D situation. Okay. So let us take one light ray. If you start from here, it is going to enter here and it is going to come and reach the final screen. Okay. So this is a single ray. Let us take the point at which it enters the object, S is equal to 0. We are going to parameterize this ray by S, okay, parameterized by S. So it enters the object at S equal to 0 and then it leaves the object at S is equal to S naught, okay. And we are basically interested in how this intensity of the light ray changes as it goes from S equal to 0 to S equal to S naught, that is basically what we are interested in, right. Now let us assume that the material has some absorptivity called mu. Okay. Now this is a general property, right now we do not have to specify what physically mu corresponds to. It could correspond to X-ray absorptivity, it could correspond to density, it could correspond to various things depending on the context, we will talk about that in a minute. But let us assume that the variable is mu, okay, and it is a function of X and Y and Z, sorry, it is a function of X, Y and Z, but in this case because it is 2 dimensional we are only looking at the YZ plane, right. Remember Y is like this and Z is like this, a detector which was originally a screen now looks like a line, it is a 2 dimensional version. So we will drop the X dependence and look only at Y and Z. Okay. So our single light ray, let us say, has an equation Y of S, Z of S, and the coordinates at the point of entry are Y0 Z0 let us say, and the coordinates here are YF ZF let us say. Okay. So you can easily write the equation of this line if you knew these 2 points, right, you can get the equation of any point on the line. But what happens to the intensity? So it turns out that a simple way to represent what happens to light intensity as it passes through materials is given by something called the Beer-Lambert law. This is an approximation, of course it is possible to derive some variant of this starting from Maxwell's equations in a systematic way. We will obviously not do that but it is physically based, right. And it says that the intensity that you see finally is the initial intensity times an exponential function of minus times the integral mu of Y of S, Z of S, ds, S going from 0 to S naught. Okay. So it tells you that the intensity is exponentially falling off as the light ray passes through the material. And this sort of makes some sense because the farther you go the more absorption is happening, and so you would expect this exponential fall off or a strong fall off to be present, and this exponential is exactly that. So I naught of course is the initial intensity you had when the light wave was entering, and IF is what you pick up on the screen. And we will assume that there is no absorption in the material surrounding the object. Of course there is a light X-ray going through air or whatever, it is practically 0. Okay. So the material property is really encoded here in mu. This is your material property. So a single ray measures the integral of the material property along a line. So you can imagine if you have a sequence of rays that go like this parallel to this ray, which is what our incoming X-ray source does, then you have a sequence of these integrals that are present on the final screen, right. So that is what you are going to pick up. So now we will talk a little bit more about this mu. The final aim, like we said, is to be able to determine mu of yz. So that is in this plane, and if you look at subsequent planes below you have a x dependence also coming in. So you want to be able to recover this, right. And the way to do this is, remember what you are measuring is an integral of mu, is to go from integral of mu something along a line to actually mu. That is basically the mathematical problem we have to solve, okay. And the way to do this is using Fourier transforms. As we will see maybe towards the end of today's session, okay. Now this mu itself, mu of yz or whatever xz depending on the direction, this can be anything, okay. It can be any physical property that is contributing to absorption. So for instance it could be density. So more matter means more electrons, which means more light is absorbed. So it could be proportional to the density in some way, and so if that is the case then you are looking at X-ray. What is typical with X-ray microtomography or in non-destructive testing, if you want to look for flaws, you want to size the flaws, shape the flaws inside a material that you can't access, then you do something called non-destructive testing. It is a very common way of figuring out and quantifying defects inside materials, especially metallic materials. It could be for instance proportional to the water content or some mineral content. Different minerals absorb different X-rays to different degrees. This is what happens in biomedical or medical CT. Where you are actually measuring mu that is proportional to this particular content. It is again sort of similar to the density but not quite the same. There is a distinction between these two incidentally. So usually when you are working with metals, the intensity and the energy of the X-rays that are incoming should be somewhat larger because their absorptivity is larger. So you use typically what are called hard X-rays over here. So these are higher energy smaller wavelength X-rays, and over here you usually use what are called soft X-rays. So these are lower energy larger wavelength lower frequency X-rays. That is just a detail you want to keep in mind. Or it could actually even be, this mu could actually even be proportional to the magnetic properties of the material. So sometimes there is a magnetic moment or a distribution of magnetic moments or magnetization you want to measure, and that it turns out is also described by the same Beer-Lambert law, in which case the reconstruction scheme that you do to get mu is actually measuring the magnetic properties, and this is exactly what happens in magnetic resonance imaging or an MRI scan if you have had the misfortune of going through one. and the techniques are somewhat similar, right. There are obviously differences from one to the other, there are some things you have to change, but the broad ideas are more or less the same. So let us start looking at what we have to do to reconstruct mu of xy in general, right, irrespective of what it represents. We will just treat it as a mathematical quantity right now. We know that we are measuring IF, we know I naught, we want to use this to invert to get mu, that is our basically our problem, y z x y whatever, some 2 coordinates in the plane. Okay, to do this we have to, like I said, use the Fourier transform. So we will just basically look at some background material on the Fourier transform before we can start using it, to make sure that everybody is on the same page. So we will go over some of the basics of the Fourier transform. Okay. So if you have a signal, we have already mentioned this at some point when discussing DIC, but nonetheless. So let us say you have a signal as a function of t is time or length or distance or whatever, it does not matter, some variable. We will for now assume it is time because it is intuitively easier to make sense of, and the term frequency also comes from assuming t is time. So let us say you have a signal like this, okay, some shady looking signal. If you want to figure out what frequency components are there or what frequency components make up this signal, then you have to convert it into a frequency domain, of course, and in the frequency domain we will represent the signal by capital X, and that will tell you what frequencies are contained in the signal, right. So this omega is frequency. So if t has units of second, then omega has units of 1 by second or hertz, and x is the frequency domain representation of x, small x. Okay. The simplest way to look at this, of course, is if you have a simple sine wave. So this is x of t is say a sin omega t, omega naught t, let us say, this is x of t, this is t, this is a simple sine wave. The frequency representation of this, if you ask the question what frequency components are in the signal, then the frequency representation is basically 0 everywhere, and then it has a large peak at omega equal to omega naught, right. So it is a single frequency peak. So Fourier transform basically is giving you the information that is contained, the frequency information that is contained in the signal, and this type of information becomes very useful. One of the reasons it is very useful is because it allows you to evaluate what are called convolutions. Again, we discussed this in the context of digital image correlation, but I will briefly mention it again, where convolutions are basically time integrals of a signal and or integrals along t, whatever t is, it could be a spatial variable also, and the corresponding representation in the Fourier space becomes a multiplication, just a product, right. So it is easier to evaluate. Now before we go there, let us look at the definition of a Fourier transform. So if you have x of t is your signal and x of omega is the frequency or Fourier representation, then you can get x, capital X from small x by doing a transform, and the transform is defined like this. Where you have an exponential I, of course, is square root minus 1, omega is a frequency, that is the variable that comes out, and t is integrated over. Okay. Notice I have put a limit going from minus infinity to plus infinity. So t does not really have to be from 0, time equal to 0, t can be any variable like we mentioned, it can be a spatial variable also, in which case it can in principle go from minus infinity to plus infinity. Okay, so this gives you x of omega. The exponential of course is obtained from this Euler relation. You have probably seen this in a complex variables course. So it really is two parts, a real part and an imaginary part, that you have to take into account. Okay, good. Now this is called the ft, or this is x is equal to ft of x, ft being Fourier transform. You can reconstruct small x if you knew capital X by doing what is called the inverse transform. Okay, and it is almost analogous looking, with the plus sign replacing the minus that was here, there over here, and you have a 1 by 2 pi factor which comes up in the 1D case. Okay, so this is what the inverse Fourier transform looks like. We will call this IFT. So your small x is IFT of capital X. Okay. So if you knew x of t, then it is as good as knowing capital X of omega, or if you knew capital X of omega, you know everything about the signal. If you knew small x of t, you know everything about the signal. So they are both equivalent equivalent representations. Okay, good. So let us look at a few different variations, and the reason these variations are important are because they come up in practical implementations. So we will look at the variations of the Fourier transform. So I am going to draw a table here. So we will have just time and we have frequency here going down. Okay. So when time is a continuous variable and the frequency also is a continuous variable, you get the Fourier transform that we just discussed. Okay, so you have x of t is 1 by 2 pi integral minus infinity plus infinity x of omega e to the power of I omega t d omega, and the corresponding expression for capital X, right. So these are two integrals. The integrals are done 1 over t, 1 over omega, and you get the corresponding representation, and this is what the Fourier transform is. So you assume that the time variable is continuous and you assume that the frequency variable is also continuous. Okay. If the time is not continuous, but time goes, or t being small t, right, if t goes from being 0 to capital T, so it is not going from minus infinity to plus infinity, it is not an infinite domain, but it is a finite domain, then in cases like this the frequency becomes discrete. Okay. And they become multiples of this what is called a fundamental frequency, which is 2 pi by t. So this is a very general phenomenon, it happens in all sorts of situations. Most common situation is if you take a string and you tie it between two fixed points and then you try to oscillate the string, you will only get certain modes, right. You will only get certain modes corresponding to certain frequencies, and so these frequencies are now discrete. But if you have a free string that is infinite string, then it can do all sorts of oscillations because it does not have to satisfy boundary conditions. Okay. So if you have a function x of t that has to satisfy, let us say x of 0 is equal to 0 and x of capital T is equal to 0, I am just using 0 as a number, it could be x naught and x1 or x1 and x2 whatever. It basically satisfies two boundary conditions. Then the frequency spectrum corresponding representation in the frequency domain will become discrete. Okay. So, whenever you have a discrete frequency representation, you do not have a Fourier transform, but you have something called a Fourier series. So, if you have taken a course in engineering maths, you have probably looked at solutions of differential equations or heat equation, and the solution often comes up in the form of a series, a Fourier series, and that is because the differential equation has a finite domain, and the finiteness of the domain means that the frequency becomes discrete, right. So, the thing that changes when you do this is in the discrete case, when you have Fourier series, you have not any frequency, but you have a discrete set of frequencies and they are given by this. Okay, there is no omega now, there is only xn. So, the n becomes like your multiple of this fundamental frequency, which is 2 pi by t. Okay. And the representation for x changes, goes from minus infinity to plus infinity. N is of course any integer, and this now becomes xn times e to the power of plus in 2 pi by t times t. So, Fourier series representation becomes like this. Your time is continuous, there is no, remember this is an integral now, so there is no constraint on this, but the frequency is discrete because you only have this index n, you only have multiples of the basic frequency, which is 2 pi by t. Okay. So, this is again the moment if you want a physical picture, this oscillating string is a good picture to keep in mind. So, this is kind of obvious, right, we have seen this in some form or the other. Now, if you look at digital signals, you are always sampling the signal at a particular frequency. So, you do not have in principle x of t with infinite resolution in t. So, what you are actually measuring is, if this is your x of t, if this is your actual signal, what you are actually measuring is at some intervals, right. Whatever device it is for you are using for recording stuff is actually measuring at some intervals, and so you really do not have an infinite or a completely continuous signal, but you have a discrete set of points that represent this signal. So, now we have to talk also about situation where this time is discrete. So, this happens when you have digital sampling. And your time now is a discrete variable. So, signal x of t is represented by a collection of values x0, x1 blah 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 up to x capital N, depending on how many samples you have taken, and so you have a discrete time signal. If you have an infinite domain discrete time signal, which means you do not have boundary conditions like this, then your frequency will be continuous because the frequency has no reason to become discrete, but your time is now discrete. When you have a situation like this, you have a variation of the Fourier transform, that is called the discrete Fourier transform. So, you still have a continuous frequency spectrum, but you have a discrete set of points in time. Okay. And now the relationship will flip. So, I am not going to write this down because we do not need it for now, you only need it for an implementation. So, we will talk about it at a later stage, but the implementation will, the representation will flip. So, now xn will be represented as an integral as a summation capital Xn. So, capital Xn will actually become x of omega and it will be an integral, it will be a sum, sorry, and small x of t will now become x of n times tau or xn, small xn, and this will now be represented as an integral. So, you flip the two equations here and you change the signs accordingly, that is what will happen. Okay. Now, it is not pragmatic to have a signal defined over an infinite domain, and so you have typically signals defined over a finite domain. So you really have to look at this last cell in this table, which is you have a discrete time, which means you have a digital signal sampled, and you also have a discrete frequency because you have a finite domain. And in this region the Fourier transform that corresponding transform that you have to do is called a finite or a fast Fourier transform. Or sometimes called an FFT. So if you open up MATLAB or Python or something, you will see a package to do FFT and not FT, and that is because you have to work with discrete signals, you have to work with arrays and over a finite domain, and so you will get something that looks like a sum in both cases. So what you will do here is you will approximate this as a sum and this as a sum over a discrete set of time points and a discrete set of frequencies. Okay. So these distinctions are important to keep in mind because they come in handy when you look at practical implementations, but for now we will skip over some of the details and move on to the actual description of how this Fourier transform comes in handy. But before we do that, I just wanted to mention one last thing, which is this idea that you have to sample. So if you have a continuous variable t, you have to sample at a certain frequency, right, and so the natural question comes up, okay, what should be the ideal rate for sampling? If you have a frequency, a sampling frequency, let us say omega s, for want of a better subscript, s for sampling, then what should the value of omega s be? Okay, and this is given by something called the Nyquist criterion. And this criterion is important to keep in mind because when we look at signals for the case of tomography, what is called the Reynolds transform, you will see that we have a t dependent signal like this and we are trying to reconstruct it from its Fourier transform. Okay, that is what we will be doing, and so you naturally need to know what the smallest resolution is that you can get when you do this type of thing, right. So the Nyquist criterion basically tells you the following. So if x of omega is equal to 0 for all omega greater than or equal to some omega n by 2. So in your frequency representation of the actual function, the values are all 0 after some particular frequency which we are calling omega n by 2, then the sampling frequency omega s must be equal to omega n, okay, and this is called the Nyquist frequency. Okay. And this tells you really that you need at least 2 samples per cycle of the fastest changing frequency in your signal. Okay, that is basically what the Nyquist criterion says. If you do not sample at this frequency or higher, you can obviously sample higher however high you want, right, but if you do not sample, if you sample lower than this particular frequency, then it will lead to data loss. You will not be able to reconstruct the signal entirely. Okay, this is something to keep in mind. Now I will end this today's discussion with a more generalized version of the Fourier transform called the 2D Fourier transform. Now so far you have not seen, perhaps it is not obvious how this Fourier transform relates to the situation we described. Remember the situation we described was this: we had a light ray coming like this or a bunch of light rays coming like this, and then you have a screen here, and then you have whatever intensity along one particular line is given by IF equal to I naught exponential of minus integral mu ds going from S naught to SF or whatever, right, or S0 or 0 to S naught. This was our problem. Now to see where we where this comes from, we won't work out the entire detail, entire bunch of details now. We will do that in the next session, but to get started, let me introduce a more generalized form or a higher dimensional form of the Fourier transform called the 2D Fourier transform. So let us say instead of x of t, I have a function mu of x comma y, okay, some function, or for generality let us use f of x comma y. Okay. The 2D transform of f is given by f of u comma v. Now you have two variables, so you have to transform in two variables, and it is given by the analogous expression. So you take f of x comma y, you do a 2D integral, but now you do minus I times ux plus vy times dx dy. So it is just if you did not know anything about Fourier transforms and somebody said generalize the 1D case to 2D case, this is the expression you would write down, right, without thinking, and it is correct. So u becomes like an x frequency and v becomes like a y frequency. So you have two frequencies now to deal with, one in the x direction, one in the y direction. Okay. The inverse transform is analogous. You have to now integrate over all frequencies with this kernel that has a positive sign replacing the negative sign, and exactly like the 1D case. It looks like this. This is the inverse transform, inverse 2D Fourier transform. Okay. Now to see where we are going with this, I want you to focus on this. So remember, u is like an x frequency, v is like a y frequency. So it has dimensions. If x is dimension of length, then u has dimensions of 1 by length or wave number, likewise v has dimensions of 1 by length. This expression can be written as u bar dot r bar. Okay. U bar is a vector, 2 component vector, it has components u and v, and r bar is also a vector which has components x and y. So r bar is like a position vector, u bar is like a frequency vector, let us say. Now this e to the power of I u bar dot r bar this function will have the same value when u bar dot r bar is constant. Okay. So when u bar dot r bar is constant, e to the power of I u bar dot r bar is constant. So anywhere where u bar dot r bar is constant, this function will have the same value. Not only that, I can add 2 pi to this constant and the exponential will get the same value. Okay. And that is really the key for starting off on the 2D problem for tomography. This value of u bar dot r bar equal to constant, this fellow represents the equation of a line in the plane, in the xy plane in this case, right. And the line is distant, let us say its constant is equal to some c naught. The distance of the line, the offset or the intercept on the y axis is given by c naught, right. Not only that, it represents, for this exponential to have the same value, it represents a family of lines all separated by 2 pi n. So if you have c naught plus 2 pi n, e to the power of I u dot r will give you the same value because e to the power of I 2 pi is equal to 1. So you now have a family of parallel lines all separated by 2 pi n. Okay. So what this means is that if you take a plane, your e to the power of I times 2 pi n is going to have the same value on a family of parallel lines that go like this. The inclination of the line is of course given by tan inverse of v by u, inclination to x axis of course, inclination to y axis is tan inverse of u by v, but you have a family of lines. So on this line, exactly on this line, e to the power of I times u dot r has the same value as it has exactly on this line, as it has exactly on this line, and so on. And if u dot r is equal to 0, let us say for example, then the corresponding orientation will change, and so you will have a different value of the exponential, but nonetheless it will still give you a family of lines. So now you see already there is some relation. Now you have a family of lines that are passing through the material, and if your cross section were like this, you could think of this family of lines as sampling the function f of x y along a particular direction characterized by a pair of constants u comma v. By changing this u comma v, by changing the orientation of the family of lines, you are sampling a different location in the frequency domain. Okay. I hope this sort of thing is loosely, at least intuitively clear. This, what I would like you to think about a little bit more. This is somewhat analogous to having the same sample and rotating the sample. If you have arrays like this, having the sample and rotating it about 180 degrees, okay, because this is analogous to having the sample and looking at a family of lines like this, looking at a family of lines like this, looking at a family of lines like this, and so on. And that is exactly what the 2D Fourier transform does. So, you now have some type of hopefully intuitive idea of where this Fourier transform fits in. So, the 2D Fourier transform is related to what you are actually doing in a tomography problem, right. So, you are sampling these integrals along those lines, and in some sense you are actually probing the frequency domain directions given by this. Okay. So, we will just think about this idea, we will start from here in the next session, we will make this a little bit more concrete, there is something called the Fourier slice theorem, we will talk about that. And once we know exactly what we are sampling and how it is related to the Fourier transform, we can then look at how reconstructions can be done and how the actual function f of xy, which in our case will be mu of xy, can be recovered. So, we will start with that in the next session.